Okay, so let's start the session now. Good evening to everyone, and welcome to this live interactive session for the course on concrete technology. My name is Selu Vinayagam, and I'm a PhD scholar in the Civil Engineering Department at IIT Madras. So I'll be handling this interactive sessions every week on Tuesdays, 6 to 8 p.m. Right. So this is our first session. So the purpose of uh, conducting these live interactive sessions is to help the students enrolled in this course, understand the concepts that are being taught and to apply them in solving the assignment problems that are given each week, right? So we will look at some questions that are based on the lecture materials that are covered in class, right? And then look at problems that are similar to what is asked in the assignments, and then see how we go about solving them, so that you will be able to solve the assignments on your own, and that will help you, finish the assignments, and it will help you with the getting good grades in the course. All right. So with that, we will start the session for week one, right? So in this session, we'll cover the concepts that were covered in the first week of this course, right? So right now, the third week content is also live, but we'll start with the first week's content. Okay. So before we get into the questions, so we'll just have a look at what was covered in the lectures of week one, right? So there were three lectures. So in the first lecture we looked at what are the we saw that concrete is a composite material, right? It is made up of different components, right? There are coarse aggregate, fine aggregate, there is cement, water, and so on, right? So there it is a composition of multiple materials, right? So that's what concrete is made up of, and therefore it's a composite material. And then we looked at how cement is produced, right? What are the processes involved, and what is the composition of the cement itself, right? So it is even made up of further uh, many other materials, right? So that's what was covered in the lecture one for week one, right? In the second lecture, then we looked at what is the structure of the different cement compounds, right? So in cement we have different compounds such as different oxides as well as the compounds formed out of these oxides. So we saw what are the structure of these different compounds, and we looked at a process called as hydration, right? So hydration is the process of the incorporation of water by these different cement compounds, right? And we looked at what happens in the hydration process, and then the different chemical reactions that occur in the during the hydration of cement, and then the hydration process in detail. And then we also looked at the bonding action. It concluded with the bonding action of the cement hydration products. And in the final lecture, we looked at what in detail the bonding action, like the different forces that are at play, such as the van der Waals forces. And then we looked at the heat of hydration, because hydration of cement is an exothermic process, right? So there is heat involved, and we looked at what is the heat of hydration of the different compounds, and what is the total heat evolution, right? And how the different compounds upon hydration contribute to the strength of uh, strength of the concrete, right, with age. And then we also looked at what something called the degree of hydration, right? So it is the degree of hydration is nothing but the fraction of uh, the cement that gets hydrated with respect to the total volume of cement that was used, right? And we also looked at different models of hardened paste structure. So how the hardened cement paste, is how what is the structure of this hardened paste. So there are multiple models that are available in the literature. We looked at some of them, and also we finally looked at the porosity of the in the cement paste, right, at the end. Okay, Anish, do you have a question? Anish, you have your hand raised. If there is a question, you can unmute yourself. Okay. So with that, now we will go on to solve some problems, right? So based on this content, right? So the first question is, which of the following properties of concrete is considered to be undesirable or disadvantageous? Right? So we have four options: low life cycle cost, moldability, low tensile strength, and robustness. Okay, so what I will do now is I'll create a poll, right? So each of you can take a minute or two to think about it, and then you can put your answers in the poll. Yeah, now I have launched the poll. Right? It is live. So once you are ready with your answers, please put your answers in the poll. Yeah, there is a question: will the recording of the lecture be provided? Yes, I will provide the recording of these live sessions. So they will be uploaded to YouTube and the links will be given to you. Yeah, instead of using the chat box, please put your answers in the poll so that it will be easier to track. Is everyone able to find where the poll option is?
It's under activities.
Yeah, it's under the activities option. There will be polls. Let me just wait for one more minute. There are some answers coming in. Okay, so we have a majority of you answering it is option C. Right? So we have one answer for B. Let's look at the correct answer now. So it is C, right? So C is the right answer for this question. So the question was, what which of the following is the undesirable or the disadvantage of using ordinary concrete, right? So when we talk about the life cycle cost, so what do we mean by the life cycle cost is the initial cost or the capital that we invest, right? So the materials and also for construction, right? Along with that, there is throughout the life cycle, right? So we have to maintain all the damages or other repair works, right? So that is the maintenance cost, right? So together the capital cost as well as the maintenance cost is the total life cycle cost, right? And this total life cycle cost is relatively lower for concrete as compared to other materials that we may use, right? So it has a low life cycle cost, and therefore it is actually an advantage, right? Because it is then cheaper to use in bulk amounts as it is required for construction, right? Therefore, it is desirable to have a low life cycle cost. And the second option is the moldability. What do we mean by moldability? Is that it is uh, we can cast concrete into different shapes that we require, right? So that's what we mean by moldability, and this is also a desirable property to have, right? So we could get any shape that we require out of it, right? So it is desirable. And we'll look at C later. D talks about robustness. What do we mean by robustness? Is that concrete can uh, tolerate or take adverse loading conditions, right? So it can withstand adverse loading conditions, and therefore it is robust to failure, right? Because of these adverse loading conditions. Therefore, that is also a desirable or an advantageous property to have. Whereas this low tensile strength, we know that concrete is good in compression, right? So we are not talking about reinforced concrete, only the ordinary concrete without any reinforcement. So that has a low tensile strength. So it can take compressive loads, but it will fail with tensile force, right? So it has a low tensile strength, which is not really desirable, and therefore that is the disadvantage of using the ordinary concrete, right? So that's the answer for the first question. If you have any questions, you can put it in the chat or you can unmute yourself and ask anytime. Okay, we'll move on to question number 2. How much CO2 is produced on an average during the production of 1 ton of ordinary Portland cement? The options are 0.25 tons, 0.5 tons, 0.75 tons, and 1 ton. Let me create a poll again.
Zero point 0.5 tons.
Okay, you can just put it in the poll. We'll look at it at the Okay, so we have some answers. So most of you have opted for option D, and there is a couple of votes for B and C as well, right? So we look at the answer now. The right answer is option D, 1 ton, right? So we have the cement production involves the release of carbon dioxide, right? From uh, uh, from the use of fossil fuel as well as from the production process itself. So we release a lot of carbon dioxide as a part of this. And if you look at it, the typical range of carbon dioxide that is released into the atmosphere is in the range of 0.74 tons to 1.25 tons, right? It's not a fixed quantity. It varies depending on the conditions and the fuel that you are using, right? So it is the typical range that we see in the production of 1 ton of OPC, right? The question is about the average. Uh, on an average, what is the CO2 that is released into the atmosphere, right? So if you look at it, the average would be around close to 1 ton, right? So for producing 1 ton of OPC, on an average, we release 1 ton of carbon dioxide, right? So this is something that you can just remember, right? So these are the typical range of values. Okay, moving on to question number 3. Which of the following compound has the maximum heat of hydration? Tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium alumina ferrite. For those of you who joined late, I create a poll for every question, right? So you can find it within the activities tab. You can cast your answers in the poll. All right, so we have a few answers in the poll. So most of you have opted for option C. There is an answer option A as well. So the right answer is option C, tricalcium aluminate. Right. So if you remember from the lectures, we it was discussed about the different the compounds present in cement and their rate on their amount of heat hydration. Right. So we see that for tricalcium silicate, it is about 502 joules per gram, or about 120 calories per gram. For dicalcium silicate, it is 260 joules per gram, or 62 calories per gram. Whereas for tricalcium aluminate, it is the largest, right? 867 joules per gram, or 207 calories per gram. And tetracalcium alumina ferrite has the second or the third highest, which is the 490 joules per gram, or about 100 calories per gram, right? So the question was about which compound has the highest or the maximum heat of hydration, right? So during hydration, as we saw, it is a hexothermic process. So heat is released, and tricalcium aluminate has the highest heat of hydration, right? 867. So that's the right answer. So what do we? So what does this tell us? By having the highest heat of hydration, it also tells us it is the most reactive of all the four compounds that we have listed here, right? So it is what will quickly react once we add water to cement, right? So C is the right answer. So question number 4, which of the following abbreviation is used for belite? The options are C3S, C2S, C3A, and C4AF. So in cement chemistry, we have very big formulas for the compounds and we use them too often. So instead of writing them every time, we use shorthand notations, right? So we abbreviate them. So which of these notation represent the compound malate?
Option B.
Yeah, okay. So we'll just wait for others also to complete. Okay, so we have a few answers which for option B, and some have also said it is option A or option D, right? So the right answer is actually option B, right? So we first need to understand the different notation that we use in cement chemistry, right? Some of the common ones is we use C for calcium oxide, we use S for silicon dioxide, we use A for aluminium oxide, and F for iron oxide, and S bar for sulfur trioxide, right? So these are the common notation that we follow. And the question was about the abbreviation that we use for belite, right? So what is belite? Belite is the name for dicalcium silicate, right? So for dicalcium silicate, it is 2CaO.SiO2, right? That is the formula for dicalcium silicate. And so if we abbreviate this, so for calcium oxide we use C, for SiO2 we use S, right? So it is C2S, right? So that is the abbreviation that we use. And similarly for alite, which is for tricalcium silicate, which is C3S, we don't have names for specific names that we use for tricalcium aluminate and tetracalcium aluminum ferrite, right? But we can still use the abbreviation. using the notation that we follow. Right? So the right option is option B. Okay, any questions? Okay. So moving on to question number 5. The major constituent of concrete that is responsible for the dimensional stability of it is dash. The options are cement, aggregates, fly ash, chemical admixtures.
Aggregate.
Okay, so let's look at the answer now. We have a majority of you opting for option B, aggregates, and there are some of you have said it is option A, cement, right? So the right answer is actually option B, aggregates, right? So if you look at the composition of cement, right? So 25 to 40% of it is made up of the cement paste, right? Whereas 65 to 70% of it is made up of the aggregates, right? And these aggregates are inert material, right? And they are also strong material, right? And therefore, it is these aggregates which provide like the skeleton of the concrete itself, and it is what provides the stability to the concrete, right? And we also have the other options such as the fly ash and chemical admixture. The fly ash, as we know, is a mineral admixture, right? And there are other admixtures that we use primarily to enhance the properties or the durability of the concrete, right? So fly ash we could use as a substitute or substituting cement, right, in concrete to some proportion. And chemical admixtures, we use them to enhance specific properties of the fresh or the hardened concrete, right? So we have different types of chemical admixtures such as accelerators, retarders, and so on, right? But it is the uh, aggregates which give us stability to the concrete, right? And they make up the major portion of the concrete, about 60 to 70%, right? So that's why option B is the right answer. Moving on to question number 6. Which of the following is a characteristic of all the cement minerals? Option A is equal sized anions and equal sized cations. Option B is small sized anions bonded with large sized cations. Option C is large sized anions bonded with small sized cations. And option D is none of the above. Okay. So instead of chat, please use the poll for answering the questions. Okay, so let's take a look at the answer. So there is almost equal voting for options B and C, and there's also one vote for option A. The right answer is option C. So in all the chemical in the cement minerals, right? So they are we can see that it is common among all of them that they have a large sized anions which are bonded with small sized cations, right? So mostly it is the calcium ions, right? So which is the cation in these compounds, and then there are the compared to the size of the calcium cations, the anion sizes are large, right? So which is the characteristic that is seen across all the cement compounds, right? Mineral compounds in the cement, and um, it is this characteristic which is what making the hydration process happen, right? So as we saw in the lectures, right? So it is this difference in the sizes between the cations and the anions that is leading to the lesser packing density, which leads to incorporating the water of crystallization, right? So that's option C is the right answer, where the anions are larger and the cations are smaller in comparison, right? So question number 7. So the line saturation factor LSF, if it is greater than 100%, what does it indicate? Options are cement quality is good. Option B is presence of free lime in cement. Option C is cement has a better soundness. And option D is none of the above. Okay, any more answers? Okay, so let's take a look at the answer. Majority of you have voted for option B. There is also some people who think it's either option A or option C, right? But the right answer is option B, right? So when the LSF is greater than 100%, it means that there is presence of free lime in the cement, right? So to understand that, let's first see what LSF is, right? So the lime saturation factor is what we call as a control ratio or a quality control parameter in the manufacturing of cement, right? So what does that mean? It is lime saturation factor is nothing but the ratio of the calcium oxide to the sum of some factor times the SiO2 plus some factor times the aluminum oxide, and some factor times the iron oxide, right? So it is a ratio of calcium oxide to the sum of the other three oxides that we see in cement, right? So when this it is expressed as a percentage. And what happens when LSF is more than 100%? How can it be more than 100 if the numerator quantity is much higher, right, than the denominator? That's when this ratio will be more than 1, and the percentage will be greater than 100, right? So in that case, what does it mean? When it is more than 100, we have more calcium oxide present in the cement, right? So more than that is required to react with or to combine with the other oxides we have present. So when we have excess quantity of calcium, so that will result in free lime being present in cement, right? So free lime means the amount of calcium that is not reacting, right? So that is excess and then remains as lime itself in the cement, right? So that's what happens when the LSF is greater than 100%, right? So typically we have it between 95 to 98%, right? So we try to keep it in that range so that the quality of the cement is good, right? So when it is greater than 100, the cement quality degrades. Why? Because it is related to option C, what we call as soundness, right? By soundness, we mean that how stable is the volume of the concrete. So when it hardens, right? So once the hydration starts, the concrete starts to harden, right? But during this process, if the volume changes drastically, right? So then what happens? Then there will be cracks formed in the concrete, right? Because of unstable changes in the volume, right? So that's what we call as unsoundness. So, right, if the concrete is sound or the cement is sound, it does not lead to that unstable changes in the volume. But having excess free lime or too much of free lime will lead to the cement being unsound, right? And therefore the quality degrades. So therefore the right option is option B. It leads to the presence of free lime. The quality will not be good if we have free lime, and it will not be sound as well, right? Any questions? Okay. So we'll move on to question number 8. The compound which is responsible for the initial setting of cement is option A, tricalcium aluminate, option B, tricalcium silicate, option C, dicalcium silicate, and option D is tetracalcium aluminoferrite. So we are talking about the initial setting of cement. Okay, so just for the sake of those who joined late, we have a poll going on after each question, right? So you can use that poll for answering the questions instead of the chat. You will find the poll within the activities option. Okay, so let's take a look at the answer. Majority of you have opted for option A, tricalcium aluminate, and there are a few who think that it is tricalcium silicate. Right? So the right answer is option A, tricalcium aluminate. Right? So we are talking about the initial setting of the cement, not about the contribution to the strength. Right? So we are not talking about the strength here. That may be why some of you said it is tricalcium silicate. We are only talking about the setting of cement here. Right? So if you can corroborate this with the heat of hydration question that we saw earlier, we notice that tricalcium aluminate has the highest heat of hydration among the four compounds that is shown here, right? And at that time I said the one with the highest heat of hydration has the highest reactivity as well, right? So when water is added, the hydration process begins, and having the highest heat of hydration can be a proxy for the reactivity of that compound. And tricalcium aluminate, having the highest heat of hydration, will be the one to react first, right? And that is what will uh, also contribute to the initial setting of cement, right? So this is also the reason why we add gypsum to cement, right? So because tricalcium aluminate can react so fast, it may not give the opportunity for the other compounds to complete their hydration process, right? So to retard that, we try to use gypsum so that the tricalcium aluminate is not completely making the cement set initially, right? So that's why it is option A, tricalcium aluminate, which is responsible for the initial setting of cement. Okay, so question number 9, this is a numerical question. So we have to calculate the volume of gel pores, and it is given that 100 grams of cement chemically combines with about 23 grams of water. We are also given the density of the hydration products as 2.51 grams per cc. The density of cement is 3.15 grams per cc, and the porosity of the cement gel is 28%. Right? So the options are 13.72 cc, 19.04 cc, 28.0 cc, and 15.33 cc. Right? So you can take about 2-3 minutes to solve it and then answer. Okay, we have a couple of answers. Wait for some more time for others to complete. We have a few answers. Does anyone need more time, or can we look at the answer now? Okay, I think then we can look at the answer. So again, a majority of you have opted for option B, 19.04 cc. And there are some answers as option A and option C as well. Okay, let's now take a look at the right answer. So the right answer is option B, 19.04 cc, right? So let me try to solve this and show how we arrive at that value. All right. So what is given to us? We are told that 100 grams of cement, right, chemically combines with 23 grams of water, right? So this is what is given to us, right? So what happens when 100 grams chemically combines with 23 grams? Hydration takes place, right? And let us assume that complete hydration is taking place here. Therefore, 123 grams of hydrated products, right, will be produced, right? When 100 grams of cement combining with 23 grams, therefore 123 grams of hydrated products will be produced, right? And what is the volume of these hydrated products? So we are given the density, right? We are given the density of this hydration product is 2.51 grams per cc, and we have the mass of the hydrated products, right? So we can get the volume of the solid hydrated products, right? How do we get it? So this is the solids produced, right? We know the density, and therefore, so 123 grams by 2.51 grams per cc, right? So if we divide the mass by the density, we'll be getting the volume, so which is approximately 49 cc. Another question. Okay, somebody asks to repeat the questions one to eight. We'll do that at the end. Okay, so first we'll complete the rest of the questions and then we'll repeat it for those who joined late. Okay, so we get the volume of the solid hydrated product, right? So we know the mass, we know the density. From that, we can get the volume of the hydrated products. And what else do we know? We are given that the gel porosity is 28%, right? So what do we mean by porosity? Porosity is nothing but the volume of voids, right, to the total volume. Right? So that is the definition of porosity, right? It's the volume of voids to the total volume, and that is given as 28 percentage, right? And what is the volume that we have? We have the volume of the solids. We don't know the total volume, right? The question is asking about what is the volume of the gel voids, right? So this is the quantity that we are interested in, right? And this value we know the gel porosity, right? So we need to know the total volume of the hydrated products so that we can get the volume of the void, right? So now how do we get the total volume? So what when the porosity is 28%, what does it mean? 28% of the product is pores, right? Which means the remaining 72% of the total volume is what is made up of the products, right? So 100 minus 28, this many percentage, which is 72%, is the volume of solids, right? So the 28% is pores, so the remaining percentage must be the solids, right? So which means 72% of the total volume is the volume of solids, right? And what is the volume of solid? We have already calculated that to be 49 cc, right? So from this we can obtain the total volume, right? So now what will be the total volume? Total volume will nothing but 49 cc by 0.72, right? And this will come out as 68.01 cc, right? So this is the total volume of the hydrated products. And now we have all the quantities that we need to calculate the volume of voids. We know the porosity, we now know the total volume. So using that, we will be able to get the volume of the gel voids, right? So volume of gel voids is nothing but 28% of the total volume, right? And which is 0.28 times the total volume is 68.01 cc, and which comes out as 19.04 cc, right? So that is given an option B. Okay, so that's how we calculate the volume of the gel voids, right? Any questions? Was that clear? So I'll repeat the process that we followed, right? So it is given to us that 100 grams of cement chemically combines with 23 grams of water, right? So this is the hydration taking place. We know 100 grams is reacting with 23 grams. So it will result in 123 grams of hydrated products, right? So that will be produced at the end of this hydration, right? And we now have the mass of the hydrated product, and we are given with the density of the hydrated products, right? So using that, we can obtain the volume of the solid hydrated product, right? So dividing the mass by the density, we get the volume of the solid product, which is 49 cc. And we using Knowing the definition of porosity, it is nothing but the volume of voids to the total volume, right? And that value for the cement gel is given as 28 percentage, right? And the question is asking us to find the volume of voids in the gel, right? And to get that, we need to know the total volume of the gel, right? But we do not know the total volume. We only know the solid volume so far, right? So we need to now find the total volume. To find the total volume, we again use the porosity information. So we know 28% is pores. So the rest, 72% must be the volume of solids, right? So 72% of the total volume is the solid volume, which is known as 49 cc, right? So using that, we can get the total volume as 49 cc by 0.72. So the total volume is 68.01 cc, right? Now we have the total volume, right? We have the porosity. So using these two, we can arrive at the volume of the voids, right? So that volume of the gel voids is 28% of the total volume, which is 0.28 times 68, which is 19.04 cc. Okay. So if there is any question, please ask. Otherwise, we can continue with the next question. Okay. There's a question on how to calculate the volume of empty capillary pores, right? So we'll look at that later. So right now, in this question, we were only interested in finding the gel pores, right? So we also this is also explained in the lectures, right? How to calculate the volume of the empty capillary pores. So that we will look at it later, right? So it's also not discussing it right now because it's also, I think, a part of the assignment question, right, which is due tomorrow. So I'll let you do that first, and maybe we can discuss that later. Okay. All right. Moving on to question number 10. C3A and C4AF are responsible for strength development in concrete. So is this statement true or false? Let me create a poll for this. Okay, so we have a majority of votes for option B. So majority says that it is false, and the right answer is it is false, right? So C3A and C4AF are not responsible for developing the strength and concrete, right? So this is what I wanted to clarify when we looked at the question on initial setting, right? So the question there was about which of the components was responsible for initial setting. So there some said that it is for the tricalcium silicate, right? So but that was not the case. So the aluminate and aluminoferrite are responsible not for the strength, but the tricalcium aluminate having the highest heat of hydration will react quickly, but it is not contributing to the strength, right? It helps in setting, but not with the strength. Whereas it is the tricalcium silicate and the dicalcium silicate, the alite and belite, which are responsible for developing strength, right? For early strength, it is the tricalcium silicate, and for the long-term strength, it is the dicalcium silicate which is responsible, right? Therefore, the question was saying that C3 and C4A were responsible, but it is not, right? Therefore, false is the right answer. Okay, so moving on to question number 11. There are two statements given here. Statement 1 says cement compounds have high affinity for hydration. Statement 2 says cement compounds are characterized by large anions and small cations and thus incorporate water of crystallization to achieve stability. Right? So the options we have to choose from are that statement 1 is correct, statement 2 is correct, statements 1 and 2 are correct, and statement 2 is the right explanation for the statement 1. And statements 1 and 2 are correct, but statement 2 is not the right explanation for statement 1. Yes, so we will share the recordings of these sessions. So we'll upload it to YouTube and we'll share the links with all of you. Okay, so these statements that I have given here are actually based on the concept that is covered in the lecture. So these are actually there in the PPTs, right? So we are only discussing the concepts that are actually taught in the lectures, right? So, so you'll be able to find these information in the lecture material that is provided to you. For if you need further information and require any reference books, you can refer to the course page, right? On the homepage of the course in the Swayam portal, you will be able to find the reference books that are given for this course. Okay, so I think we can now look at the answer. So before that, let's just see each of these statements individually and find out whether they are correct or not. Okay, so statement one says that cement compounds have high affinity for hydration. Right? We know that this is true. That cement compounds do react with water, right? So that's the hydration process and form the products of hydration, right? So we saw that we saw the heat of hydration in that, and at that time we saw that during the hydration process heat is evolved, and based on the level of heat of hydration, the reactivity is changing, but still all of these compounds have high affinity for hydration. So statement one is true. Statement two says the cement compounds are characterized by large anions and small cations and incorporate the water of crystallization to achieve the stability, right? So we saw this in one of the previous questions, right? What is the common characteristic that we observe in the structure of the different cement compounds? And there we said that it is in fact the large anions and the small cations that is common between the cement compounds, right? So that part is okay. The second part of the statement says that the cement compounds incorporate the water of crystallization in order to achieve stability, right? So to do that, first we need to know about the stability of these cement compounds. Because of this large difference in the size between the anions and the cations, right? The cement compounds do not cannot achieve uh, the required packing density that is required for being stable, right? So that is so they by themselves are not stable because of this size difference, and therefore if they have to become stable, the size difference has to be reduced, and that is happening when water comes in contact and hydration takes place. So the water is incorporated into these compounds, right? So that's what we call as the water of crystallization. And by incorporating this water of crystallization, the size difference between the anions and the cations is reduced. Right? So we are artificially expanding the size of the cations by incorporating the water, right? And by doing so, the size difference is reduced, and therefore the required packing density is achieved, and therefore stability is also achieved, right? So statement two is correct, and there is also another part we need to know whether statement 2 is explaining statement 1, right? And that is also true. Statement 1 is the right explanation because the high affinity is coming because of this need to incorporate the water of crystallization for reaching stability, right? So everything reacts in order to become more stable, right? Therefore, this reaction is taking place so that stability can be achieved, and therefore that is what is explaining why there is a high affinity for hydration in these different cement compounds, right? So statement one is correct, statement two is correct, and statement two is also the right explanation for statement one. Right? So the correct answer is option C, right, which is given. Okay, any questions? Okay, so we'll move on to the next one. Question number 12. Which of the following are the products of cement hydration? So we have four options: C3S, C3S2H3, CH, C3. So I'll create a poll again. So this is a multiple answer question, so more than one option could be correct in this case. So let me just create a poll. I just created four options, either AB or CD, BC or AD. Okay, please make use of the poll for answering instead of the chat. Okay. There is almost equal vote for two options. So 6 votes for options B and C and 4 for option A and B. Right? I see why that is happening. Some of you are not clear with what is asked in the question. Maybe that's causing the confusion. But we'll just wait for some time and look at the answer. So the question is the products of the cement hydration, right? It's what is coming out of hydration, right? It's the output and not the input. Okay, I think now we can look at the answer. So as most of you have answered, it is options B and C which are the products of hydration, right? So option A and D. So what do we mean by the product of cement hydration is we have the different cement compounds and hydration takes place, right? And the products of hydration are nothing but what is the output that is coming out of this hydration process, right? Once hydration happens, what we end up with is what is the question is asking, right? Not what is getting hydrated, right? So what is getting hydrated are the tricalcium silicate as well as the tricalcium aluminate given in this option, in this set of options, right? So those are what is getting um, reacted during the uh, hydration process. And as a result of the hydration, finally, what do we end up with is the CSH gel, which is represented as C3S2H3 and carbon hydroxide, right? CaOH twice. Right? So those are the products of hydration, right? What we get out of the reaction. So the reactions are given here. So we have the tricalcium silicates as well as the dicalcium silicates. So they get hydrated, so they react with water, and as a result, they give the CSH gel as well as the carbon hydroxide, right? So that's what is those two are the products that we are getting out of the hydration, and it is not what we are starting with, right? So I think that could have confused some people, right? So we are talking about what is coming out of the reaction and not what is going into the reaction, right? So the right answers are options B and C. Okay, any doubts? Okay. So moving on to question number 13, another numerical problem. So we have to find the rate of heat hydration of belite if 33.4 kilojoules of heat evolved in the hydration of 8.1 grams of C3A and 40.58 grams of C3S, 12.45 grams of C2S, 6.825 grams of C4AF, and we are also given the rate of heat of hydration for C3S as 500 joules per gram, for C3A it is 865 joules per gram, and for C4AF it is 420 joules per gram. Right? So the options are 250 joules per gram, 260 joules per gram, 245 joules per gram, and 270 joules per gram. So please take 2 to 3 minutes, think about it, and you can put your answers in the poll. some answers coming in. I'll wait for some more time.
Hello, sir. Good evening, sir.
Yeah, good evening.
Yeah, myself, Durgarao. Right now, I am research scholar in JNTU Kakinada in Andhra Pradesh.
Okay.
Sir, my question is, I'm not asking about this assignment, sir. I have some research questions regarding. Will you possible to give the information regarding, sir?
Uh, so yeah, we'll keep those discussions which are outside of this to the end of this session. Okay.
Yeah, okay, sir. Okay, thank you.
Yeah. We have very few votes so far for this question. Actually, this is the easiest of the two numericals that we have seen today. Maybe one more minute. Somebody is near completion. So let's now take a look at the answer. So the right answer is option B, 260 joules per gram. Okay, it is option B. Now let's see how we arrive at this. Reshare the screen. Okay. So what is asked in the question is we are given the total heat that is evolved during the hydration process, right? So that is 33.4 kilojoules, and we have four compounds that are that are participating in this hydration process, which are C3A, C3S, C2S, and C4AF. And for each of these compounds, we know what is the mass that is getting hydrated, right? So that is given to us, and we are also given the rate at which the heat during this hydration process is evolved from each of these components, right? C3S for C3A as well as for C4AF, right? So this is the information that is given to us. And the question is, what is the rate of heat of hydration for belite, right? So we have four compounds. For three of them, we know the heat of rate of heat hydration. For one of them, we don't know, right? So what is belite? It is dicalcium silicate. We saw earlier, right? So it is the only compound for which we are not given with the rate of heat hydration, right? So for C2S, we need to find what is this rate of heat hydration value, right? So how do we get that? Um, so the total heat evolved, right, during hydration is nothing but the individual contributions from the different compounds, right? Say Q1 is the heat of hydration rate for C3A, okay, and let us say Q2 is the rate of heat hydration for C3S. Okay, so the rate is multiplied with the mass that is getting hydrated, right? So the rate is nothing but per unit mass, what is the heat getting released, right? So for if x grams is going to react, it will be x times that rate, right? So if the rate is Q and the mass is given by this is given by the abbreviation, then it is the product of the two, right? And then we have what else? Q3 times we have also dicalcium silicate, which is the light, and we have Q4 into C4AF, right? So these are the four compounds that are getting hydrated. Each have their own rate of heat hydration, and we know the if we know the mass of each of them, then the total heat will be nothing but the sum of the product of the rate and the mass, right? So in this, what do we don't know? We know the total heat evolved, right? So that is given to us as 33.4 kilojoules, and we know the mass of all the four compounds. So all these four quantities are known to us, and we are given three rates of rate of heat of hydration, which is for C3S, C3A, and C4AF. Right? For C3A, C3S, and C4AF, we know the Q values, right? The question is about finding Q3, right? So Q3 is the unknown in this equation. So it is simple. We have one equation, one unknown. We can solve that easily. So the total heat is 33.4 kilojoules, right? Which is nothing but 33,400 joules, right? So we'll keep everything in joules. For C3A, what is the rate of heat of hydration? It is 865 joules per gram, right? So it is 865 times the mass of C3A, which is 8.1 grams. So 865 joules per gram, right? Times 8.1 grams plus for C3S, the rate is 500 joules per gram and the mass is 12.4. Mass is 40.58 grams, right? So it is 500 times 40.58. 500 joules per gram times 40.58 grams. For C3S, we don't know the rate, right? That's what we want to find out. So let's say that is X. So times what is the mass of C2S getting hydrated? It is 12.45 grams, right? 12.45 grams plus Q4 into C4AF. Q4 is 420 joules per gram and the mass is 6.825. So 420 times 6.825 per gram times 6.825 grams, right? So this is the equation that we have for the total heat evolved. So we know the total heat evolved, we know the individual masses and also the rate of heat of hydration for three quantities. For one quantity it is not known, we can easily find that out, right? So if you just solve this equation, right, you just have to find the products of these three terms and then subtract it from the total heat, divide by 12.45. So finally you will end up with X, which is the rate of heat of hydration, the rate of heat hydration of belite, which we are using, calling it as X in this equation, will be 260 joules per gram, right? If you solve this, you will find out that it will be equal to 260 joules per gram, right? So we are just using the simple equation The total heat is nothing but the sum of the contribution coming from each individual compound, and for each individual compound we know the unit uh, per unit weight of the compound what is the heat being released, right? And then we multiply it by the total mass of that compound, we get the total contribution of that particular compound. With this we have to do for each of the compounds, sum them up to get the total heat that is evolved during the hydration, right? And we are given all these individual values except for one, which is the Q3 value, and that we can easily find out by solving that equation. Okay, any questions? Okay, so there is no question, we'll continue. So question number 14 is, how does the degree of hydration change with age? The options are, it increases at an increasing rate, it stays constant, decreases at an increasing rate, or increases at a decreasing rate. Okay, I have launched a poll, you can put your answer in it. finally, we have a question where we don't have a clear majority. There is a mix of responses we have. Okay, let me just wait for one more minute as some more people are answering. Okay, so no more answers. Then let us look at the correct one. Okay, so the right, so most of you have said it is either C or D, right? So there are some answers for A and B as well, but most think it is either C or D, right? So it either decreases at an increasing rate or increases at a decreasing rate, right? So you'll see the right one is actually it option D. It increases at a decreasing rate. So you may remember this graph from one of the lectures, right? So here we have plotted the degree of hydration with the age of the cement paste, right? And we see that this is increasing, so that is clear, right? So it is increasing with age. The value of the degree of hydration is only getting higher as the age increases, right? So that is clear. So that rules out options B and C. So it could be either A or D, right? So to choose between those two, we have to look at how quickly is this increase happening. So for 1 unit increase in age, right, how what is the how quickly is the degree of hydration changing, and how is that 1 unit change at different ages, right? So we see that initially we see that there is a quick increase with age, right? So for smaller increase in age, we have larger increases in the degree of hydration. But as the age increases, we see that the increase in the degree of hydration keeps slowing down, right? It is going towards the saturation value, right? So the increase is not much when the age is increasing. So which means that the increase is at a decreasing rate, right? So the increase, it is increasing, but it is increasing at a slower pace as the age increases, right? So it is the option D, which is correct, right? So why is this happening? So let's see why is that the case. So to do that, we first need to understand what do we mean by the degree of hydration, right? So what do we mean by the degree of hydration? So if let us say if MT, right, if MT is the total mass of cement, okay, that we had initially, let us say, and if MH is the mass hydrated, okay. So we start with some mass of cement, right, and with time some of it is going to get hydrated as we add water, right? So let that mass be MH. So at any given point in time, if MH mass of cement is hydrated, then the degree of hydration is nothing but the fraction of the mass that has got hydrated. So which is nothing but MH by MT, right? So this is the fraction of the cement that has got hydrated, right? So MH out of MT has got hydrated, and that is what we call as the degree of hydration. So what happens? Initially, nothing would have got hydrated, right? So it will be zero. Once it comes in contact with water, there will be some mass that is getting hydrated, but because there is nothing that has hydrated, the total mass has a high affinity for hydration, right? So some compounds will quickly react, right, and will quickly form the hydration products. Therefore, there is a higher degree of hydration initially, right? But as time passes, once those highly reactive compounds have got hydrated, the remaining mass will slowly get hydrated with time, right? So this MH will keep on increasing, and and what is the maximum value of this MH? It cannot be more than empty, right? What we started with. So that is the maximum mass that can get hydrated. So there is a limiting value for this degree of hydration. That's why we see that this cannot grow unboundedly. It has to reach towards some limiting value, and the maximum it can go is 1. When all the cement has completely hydrated, this degree of saturation will be 1, right? So it cannot be more than that. So it cannot grow unboundedly, and with time, the reaction will also slow down. Therefore, the degree of hydration will also reduce with time. Therefore, we see that the trend of degree of hydration is increasing at a decreasing rate. Okay, any questions? Okay, so if there are no questions, this was the last question for this particular session. Okay, if you don't have any questions, we can stop the session here. Okay, and if you have any doubts, you can stay back. I will stay back for a few more minutes. If you have any doubts, we can discuss that. Otherwise, we'll stop this session here and continue again on next week, right? Same time on Tuesday, 6 to 8 p.m. Okay, right. Okay. Thank you for attending, and I'll just stay back for a few more minutes if you have any questions. And for those who missed the initial 8 questions and asked to repeat, so we are recording these sessions, and therefore we'll upload this to YouTube. You can take a look at it, look at the recorded lectures, and if you have any doubts, we'll discuss that at the start of the next week, or in the meantime, you can also make use of the discussion forum to get your doubts clarified. Yeah, the link we will give it once we upload it, right? So after we upload only, we will get the link. Yeah, week 2 discussion will be in the next week. So each week we'll cover the contents of one particular week. So this week we did week 1. Next week we'll do week 2's content. Yeah, also the PDF of this presentation that I have used will also be shared with you. So both the link for getting this PDF as well as the video link will be given to you. So please wait for some time. Yeah, this week I think tomorrow is the deadline for the submitting assignments for week 1 and week 2. Yeah, so you have to submit it by tomorrow for the first 2 weeks. For the third week's assignment, you still have some more time. The answers will be shared with you once the deadline is over, right? So once the deadline is complete, the answers for the assignments will be given to you. Okay. If you don't have questions, you can feel free to quit the session. Yes, this presentation will be shared with you. Durgarav, I didn't understand. What do you mean by video link for week 1? Are you talking about the video of this particular session or the lectures? Okay, so the week one solution video. So solution video will not be given, but the solutions as a PDF will be shared with you. But after the deadline for the week one assignment is over, right? So tomorrow is the deadline. So once you submit the assignment before that, and once the deadline is over, the solutions will be given to you. Okay. So okay, if there are no more questions, so let's stop the session, and we will meet again the same time next week. Okay. Thank you all.